In this lesson, we're going to look at simple harmonic motion, the kinematics of that motion, and how it relates to things we already know. You'll learn as we go through this that a lot of what we know about rotation and circular motion applies. So the first thing is the simple harmonic oscillators. We already investigated these, a mass spring system and a simple pendulum, which are kind of our basic ones that we focus on. But you can also have what's called a physical pendulum. And a physical pendulum is something that oscillates in the same way, but instead of being just a simple ball at the end of a string, the entire thing moves. And this, in order to analyze that, we'll need to think about moment of inertia and what we've learned from rotation. It's also other things, right? If you just have a ball rolling at the bottom of, a bowl back and forth, that could be a simple harmonic oscillator. A lot of the mechanical wave systems we think about, right? If you think about the sound generated by a speaker vibrating, that kind of thing can also have, waves generated by a simple harmonic oscillator, which is kind of interesting as well. It turns out that a simple pendulum and a conical pendulum, and you may recall when we did the conical pendulum investigation that the simple pendulum and a conical pendulum that go out to the same extremes actually have the same period. So there's a lot of stuff that we already know about circular motion that applies to this kind of motion for a pendulum. And so we want to kind of put those things together, the connection to what circles do and what simple harmonic oscillators do. So here's a little video just to show you kind of how circular motion and uniform circular motion and simple harmonic motion can be the same, right? If you're watching a spring tuned correctly and an object going around a circle, you'll notice the radius of the circle is kind of the maximum displacement of that mass from equilibrium. There's that little equilibrium line. When it's up at its highest point, it's at the top of the circle, and so on. And they track, right? And if we rotate that circle, so we're really not seeing two-dimensional motion anymore, right? We're really just looking at it kind of going up and down. You notice they follow each other perfectly, which is kind of an interesting result. So simple harmonic motion can be thought of as the projection of uniform circular motion to a single dimension. And we're going to use this idea to help us kind of graph the motion of a simple harmonic oscillator, the position as a function of time. So if you imagine something moving around in a circular path, I'm going to move myself to this corner, we know from rotation and circular motion that we can talk about the angular displacement, right? We can talk about the angular velocity, and we could think about if we were to use the x position as just one part of that kind of circular motion, we could talk about that one there. So if you look at the delta theta is omega t, right? And if you track where it is on the x-axis, that's just really part of this triangle. And so the x position is going to be the maximum, or the radius, right? The radius of the circle is the maximum x position you can get, times the cosine of theta, because that is the angle we're always dealing with. And so then if we talk about x as a function of time, it's going to be the maximum x you can have, or the amplitude we call it, right? That's the radius of this circle, times cosine of omega t, because omega t is the amount of theta. So what we're doing here is we're really taking what we know about circles and then what we know about triangles, and we're putting those two things together to come up with this argument. And I'll move myself out of the way again. But you see, you go between a maximum negative displacement and a maximum positive displacement. And that is what we call the amplitude of the oscillation. In the case of a circle, it's really just the radius of the circle. But when we're talking about a single dimension motion, that's what we get, right? So it goes around and around, and it goes back and forth in the x direction. So because we can talk about simple harmonic oscillators as if they were circular motion, there's an amplitude and an angular frequency. Even though it's not really rotating, we can think of how fast it goes through a cycle as being an angular frequency or angular velocity. We called this omega angular velocity when it was a physical object rotating, but now we call it angular frequency because nothing's actually rotating, but it still behaves in the same way. So we have our position, our amplitude, the maximum displacement. We have the angular frequency in radians per second. And since a radian is not really, a unit of physical measurement, a physical distance, that works out nicely. So there's another way to define simple harmonic motion, which is that it's motion where you can basically graph its position as a function of time as a sinusoid, right? If it looks like a sine cosine graph in its motion along an axis, then that is simple harmonic motion. So for example, myself out of the way again, right? If you look at different points in time at 0, 1, and 2 seconds for this amplitude pi, or angular frequency pi graph here with a max amplitude of 1, right? We go from 1 to -1 and back and forth and back and forth and back and forth over the full cycle. So a couple things to notice here. This is a position time graph, right? Nothing is actually waving. It's not actually a wave. This is just describing the motion going left and right, left and right, left and right. Right? It's not actually going up and down. This isn't a graph of physical position in space, x, y. It's just position versus time. So what do we know? Well, when we talk about an oscillator, there are a couple different things we can talk about. We can talk about the angular frequency, we can talk about the period, and we can talk about what we call the natural frequency. So period and natural frequency are reciprocals of each other, and this is what we would actually time with a stopwatch and count. Whereas the angular frequency talks about, well, one cycle is 2 pi radians. And so that's why it's defined as 2 pi over the period, or 2 pi times the natural frequency. So if we look at this a little bit further with a particular equation as an example, what is the angular frequency of this? What is the period, and what is the frequency? Well, we have pi in the angular frequency spot in the equation. We know that the period, right, or the angular frequency is 2 pi over the period, so we can find the period, and then we can find the natural frequency. So if we look at this graph, can we then, like before we went through and we said, oh, we have an equation, can we make a graph? Here we have a graph, can we get an equation? Well, sure. The period is the amount of time it takes to go from one peak to the next. So we would need to know that, and either it would be something we could read off the graph or have it given. So angular frequency is 2 pi over the period, so that's 4 pi radians per second. The amplitude here, reading off the graph, is 0.05 meters or 5 centimeters. And so we could write this as position as a function of time is 0.05 cosine of 4 pi t. Right? The key things being the amplitude and the angular frequency, which we can read from the graph. There's one other piece to this, and that is what we call the phase angle. What if we don't start at 0? What if we don't start with it at max displacement? Well, in that case, we have an additional piece. And you know this from math and looking at sines and cosines, that you can shift the sine or cosine graph by adding an angle inside of that cosine. And so what we do is we write it this way. We say omega t plus phi, some phase angle. This is the initial theta, the initial location. But since there isn't actually an angle here, we need to think about what that means, right? If we have a positive phase angle that we add to it, what does that do to the graph? Well, if you have a plus phi in there, it actually moves the origin to the right, further into the cycle, right? Because we're already further along in time in terms of our period. So we would start, instead of up at maximum displacement, maybe we start at 0 displacement. This is a phase angle of pi over 2, right? Because pi is half the period and 2 pi is the full period, is the full cycle, and that's a quarter cycle. All right, so it would look something like this. It's as if we started timing a quarter cycle later. If you have a negative phase angle or negative phi, right, the origin moves to the left. This is a quarter cycle. And it's if we start the clock a quarter cycle before we're at maximum displacement. So we look at two different graphs here. We have blue, which has an omega of 2 pi over 4, or pi over 2 radians per second. And then we have our equation of that is 1 cosine pi over 2 t. And red is the exact same amplitude and angular frequency, but we have shifted it over by a factor of negative pi over 2 because it looks like we started early, right? We started early. So these two simple harmonic oscillators are out of phase by pi over 2 or 90 degrees, a quarter of a cycle. The next piece would be talking about the velocity and acceleration, right? We know that this has a minimum and maximum position. It reaches those, goes up back and forth and oscillates between them. But if we have an equation as a function of time for position, we should be able to talk about the acceleration. And so here's another video for us, kind of looking at this, right? We have our position, and you'll notice when you're at maximum position, your velocity is 0 because you're turning around, right? You're crossing the velocity axis. And that your acceleration is always in the opposite direction of your displacement, right? When you're displaced really far up, you're being accelerated down. When you're displaced really far down, you're being accelerated up. And so graphically, it looks like this, right? Displacement, velocity, and acceleration. And you'll notice that these are all, sine, cosine graphs. And so if we look at the maximum displacement, that gives us 0 velocity. And when we get back to the origin, 0 displacement, we have a big negative velocity. The slope is negative. Then we get to our max negative displacement. We have 0 velocity again. The velocity is going from negative to positive. When we get the acceleration, the same kinds of things happen. When you're at maximum positive displacement, you have maximum negative acceleration. When you're at 0 displacement, 0 acceleration, because you're not stretching or compressing our spring or displacing our oscillator, and again, at the top. So with calculus, we can do this too. We can take the time derivative, and we get our velocity graph is negative omega xm times the sine now. And then if we take that graph again, we can think of that omega times xm as the max velocity, the amplitude of the velocity, which is nice. And that's kind of the relationship we think about. What is our maximum velocity? It occurs when sine is maximum here, either positive or negative. And this is our relationship similar to v equals omega r, kind of what we've done before. We can go a step further. We can take the velocity and take the time derivative to get the acceleration, and we get this negative omega squared xm. And so what that means is the maximum acceleration occurs whenever cosine is maximum, which is the same times that position is maximum, but we have a negative sign, so it's in the opposite direction. And so the maximum acceleration is omega squared xm. Kind of looks like centripetal acceleration, actually. There is an interesting result, though. If you compare the acceleration equation and the position equation, you'll notice that the xm cosine omega t plus phi is exactly the same. So you can think of the acceleration as just negative omega squared times the position. And this will actually really be helpful when we get into the dynamics of it, looking at acceleration, because the acceleration is not constant. So we can't just use Newton's laws and kinematics for this. More on that in a little bit. So position, velocity, and acceleration of a simple harmonic oscillator. They follow these sine, cosine, and sine graphs, right? They are the time derivatives of each other. They look like that. Important things, though. Acceleration is not constant. Kinematics equations do not apply to simple harmonic motion, at least not the way we've used them. There's a way to use calculus. That's what we're going to be thinking about, but we cannot just apply the kinematics. All right, so wrapping up simple harmonic motion kinematics, there's a lot of similarities to circular and rotational motion. They are periodic. They are sinusoidal when we graph them, position versus time, and velocity and acceleration. But because acceleration is not constant, you can't use your kinematics equations. You have to use calculus.